Sounds good. Let's finish epoxides. We found the 3 ways that we can synthesize epoxides. And really, 2 of those 3 ways were actually the same way. It was the halohydrin elimination to the epoxide. What I demonstrated was how you can show it as 2 steps, or you can start right from the halohydrin. Let's talk about how we react with epoxides. As a reminder, reactions with ethers, very limited. Ethers are quite stable, not reactive to a lot of things. Ethers don't behave as good leaving groups. Ethers don't behave as good nucleophiles. Ethers don't do much. But if you protonate an ether, then sometimes you can cleave it and turn it back into an alkyl halide. Epoxides, on the other hand, go through ring opening. Because they have that angle strain of being a 3-membered ring, it's actually quite easy to break one of the bonds in the epoxide and go from a ring to not a ring. When we do a ring opening, I just want to try and point this out. There are 2 carbons of the epoxide. The ring opens because a nucleophile attacks one of those 2 positions. So if the nucleophile here attacks carbon 1, well then carbon 1 is the side that opens. Carbon 1 needs to lose a bond now, so the bond between 1 and the epoxide breaks open. This should remind you of the halonium ring intermediate. When we're doing halogenation of an alkene, we form the halonium ring, we attack one side of that ring, and we open on the other side. This means that of positions 1 and 2, this new group gets added to position 1, and an oxygen group gets added to position 2. Well, I guess the oxygen group was already there at position 2. Now, in basic conditions, and by basic I mean the epoxide has not been protonated because there's no acid present. Nucleophilic or basic conditions means that our oxygen opens to be negatively charged. We'll talk about whether it's negatively charged or not, but what I want to draw your attention here, what I want to draw your attention to is that we have this vicinal I want to say alcohol because a lot of times we're going to protonate it to become an alcohol, but it doesn't have to be an alcohol. Notice how this is set up well for the Williamson ether synthesis, essentially. SN2 with an alkoxide. I could use this O- to make an ether. I could use it to get an alcohol. I could, well, those are my 2 options. So it's basically a vicinal new group plus alcohol. What does vicinal mean again? What are we describing? That.
2 carbons and they have the groups.
Exactly. They're in the same vicinity, as opposed to being on the same carbon, which would be geminal. This is not a geminal addition, it's a vicinal addition. There actually is no geminal addition. It doesn't really work that way. So nucleophile opens one position, oxygen is added to the next. When you are doing a synthesis and you're wondering whether an epoxide makes sense to use or not, try to figure out whether there's a vicinal set of groups. Is there a new carbon-carbon bond plus an alcohol vicinal? Is there a new ether plus an alcohol? Is there a new oxygen plus an alcohol? A new nitrile, a cyano group plus an alcohol? That's the framework of an epoxide ring opening. It gives you a new vicinal group of things. So on this map, you can see that most of the options are written as this or this. Of the 5 reactions with the epoxide, how many don't have an or option? Just one. What is the difference between the ors? When it says there's one option or a second option, what's the difference between them? Sorry, I wrote it on the board, but you can't cheat. Right, one set is acidic, one set is basic. The other thing I would have maybe wanted you to see is that one set of reagents is a 1-2, a 2-step process. First introduce this, then do an acid workup. First introduce hydroxide, then do an acid workup. First introduce alkoxide, then do an acid workup. Or introduce an alcohol in acid. Introduce a water in acid. Introduce HBr. Why is it that the one option that doesn't have an or doesn't have an or?
Can you not use organometallics
Organometallics
in acidic conditions?
don't exist in acidic conditions. Can't use them in acidic conditions because anything slightly acidic will have its proton ripped away by that nucleophilic carbon. Organometallics have to be nucleophilic conditions, whereas bromide can be acidic or nucleophilic. Hydroxide and water can be acidic or nucleophilic. Cyanide can be acidic or nucleophilic. Organometallics cannot. So acidic conditions, things like hydrogen cyanide, hydrobromic acid, water and acid, alcohol and acid. Acidic conditions will first protonate the epoxide. Now we've talked about how we're not going to show a lot of mechanisms in this unit, and by not show, I mean you're not going to be tested on any of the mechanisms from this unit. Your midterm will test you on your NAS and EAS mechanism. Now when we protonate an epoxide, the oxygen becomes protonated. It should look to you a lot like our protonated ether because it is quite similar. But I want to point out a feature of the protonated epoxide that impacts the regiochemistry. If the two carbons are not equally substituted, and I know that in the example I've drawn they are. We can change that by just adding R groups and making it look a little bit different. If the two carbons are not equally substituted, then the protonated epoxide is not symmetric. And you can see this on the bottom of this worksheet where it says regiochemistry of epoxide ring opening. Justice, I think that question you asked was great. Why is it sometimes it attacks more substituted and less substituted? What is that regiochemistry? In the acidic conditions, notice how I have this in the diagram. The epoxide is lopsided. It's not a little isosceles triangle anymore. It elongates the bond length to the more substituted carbon. That's not something new to you. You've actually seen this before when we had the bromonium ring. We said that the bromonium ring is lopsided and that the bromine actually sits closer to the less substituted carbon and further away from the more substituted carbon. And if you remember in the bromonium mechanism, the bromination mechanism of our alkene, if we have something like halohydrin addition or haloether addition, where water or alcohol serve as the next nucleophile, the regiochemistry is always predicted as the nucleophile attacking at the more substituted carbon, opening the bromonium ring from the more substituted carbon. And that's because that bond length is already stretched to the more substituted carbon. That bond is already easier to break. But why? Why does it stretch the bond to the more substituted carbon? Why doesn't it ever stretch the bond to the less substituted carbon? Stretching a bond is going to decrease the electron density at that carbon. If the electrons that were shared between carbon and oxygen now have to be shared between carbon and oxygen over a longer distance, you think carbon keeps them the same amount? Carbon, being less electronegative, has to give up the electrons to oxygen anyways, and now oxygen is further away. So this creates a larger partial positive on the carbon than there was before. The partial positive on the other carbon stays approximately the same, but now the partial positive on the more substituted carbon is larger. And we know that more substituted carbons hold on to their positive charge more readily, more easily, because they have more electron density to stabilize that partial positive. And it's the same thing here. There's a bigger partial positive on the more substituted carbon because it can stabilize a partial positive better. So on your worksheet, I've given you this transition state. If the nucleophile opens, the only thing I didn't add was the double dagger. Got sloppy. That double dagger just helps us remember we're looking at a transition state, not a structure you can isolate, but a theory of how bonds are forming and breaking. And in this transition state, the positive charge is essentially at the carbon. And where is a positive charge more stable? At a more substituted carbon. So the nucleophile opens the ring from the more substituted position because it stabilizes that positive charge the most. The other type of condition is basic or nucleophilic conditions. This is where we can show cyanide or bromide or hydroxide or alkoxide or organometallics. And to get an alcohol at the end of it, if you want to open your epoxide to an alcohol, and you actually don't have to protonate it to an alcohol, you can use it to do an ether synthesis. If you protonate the oxygen to an alcohol, basic conditions require that aqueous workup. which is why you'll see for all of those, oh, I didn't do it for all of them, did I? Yeah, bummer. First alkoxide, then acid. First, oh, I forgot my negative charge on the hydroxide too. Just what can you do? I'm going to just sketch out some of the mistakes I made on this. That is a mistake. I didn't put my hydroxide. And over here, I actually put that you could just do KCN, but you would need first KCN, then H+. Love it. I made this Monday. One day? Yeah, that's the problem, right? I made it quickly. I am still trying. All right, so in basic conditions, our nucleophile doesn't wait for the ring to be protonated. Nothing's coming to protonate the ring. Nothing's coming to protonate the epoxide. So the nucleophile attacks at the less substituted position. Again, assuming that one of these sides is more substituted than the other. And this is what gives us the other transition state, where essentially a negative charge is held by the carbon. So I think this would be a good time to remind ourselves, positive charge, more stable on a more substituted carbon, because that lack of electron density is swarmed by electron density. So the positive charge is stabilized. Negative charge is more stable on a less substituted carbon, because that excess of electron density has very little electron density around it to repel against and be destabilized by. Opposite charges should show opposite stability patterns. You guys agree with that? Opposite charges, opposite stability. Remember, this is just a transition state. It doesn't exist. What we isolate is the alkoxide, and this is why we need a second step, an aqueous workup that we can use to protonate the oxygen and isolate our alcohol. And that's it. Those are all the things for this unit. So we have an hour and 10 minutes to solve the remaining 6 syntheses, which focus on epoxide, and ethers. And then I'm just going to hand this out now, a roadmap worksheet. And as a reminder, one side of the roadmap, just filling in reagents. One side of the roadmap, just filling in products. I didn't upload it yet. You looked and you know, don't you?
Yeah.
You're welcome. I think that it would be beneficial for you guys to do something similar to yesterday, where you work in groups to solve a synthesis, and then we come back together to talk about them as a whole. Are you guys down for that?
Yes.
Okay. Since we've got this small group, we've got 6 syntheses, but one of each length, 2, 3, and 4 step. I guess I'm kind of thinking 2 groups of 3, and both groups just tackle one side. If that's too big, though, and you'd rather work just one-on-one with somebody else, we can do 3 groups of 2. Yeah? Jaylee, can I have you work with Evan and Justice? And Evan, can I have you work with Jordan and Mimi? And I'll come around and answer questions. Oh, fair enough. Why don't you guys do the left-hand side, and you guys can do the right-hand side. Okay?
Okay, guys.
I'm working with everyone.
Everybody caught a lunch. I'm awake today.
A mega group?
Yeah, well,
I was struggling yesterday.
you're just like, Evan, you work with them, and Evan, you work with
I know. You know, my brother Sam married a girl named Sam,
Oh, really?
and so we call them the Sams. And when we're like in a big group and we really need to differentiate them, we call her Sammy. But she doesn't like going by Sammy. Like that's not her name. Her name's Sam. So we refer to, well, I do my best to just refer to the both of them as Sam, and just use context to figure out which Sam I'm talking about. Sam, did you bring Sam's watch? You know, it's just fun to be able to say it unironically too. Jordan, I'm uploading the roadmaps now. Thank you. Well, for the roadmap, you start at the only structure given,
Oh, okay.
methyl cyclohexane, but you guys are doing the syntheses first, not the roadmaps.
Gotcha.
No, not that. This, Evan.
Gotcha.
Okay. Yeah, maybe I should have waited on the roadmap.
I think if you do the NaOH, it'll flip the regiochemistry of the.
That's what we have to do. We have to change at least the stereochemistry of it. Because now it's lead instead of
Then couldn't you just change?
Attack at the most sun position. We have to add an OH.
yeah, so that would technically work though, because I would push this guy to the back, or to the front, I guess, and this guy would do an NaOH.
Yeah, but we already started that.
Yeah, okay, I was.
I'm just trying to think of the other one.
Can we do like a, just basically like what he had, KCN?
Yeah, can't you just do the same thing?
You could, I think you could.
Okay, the roadmap practice is on Canvas.
So I have in my notes, you can use NAS and substitution.
Yeah, for your first one.
I think we could just.
Is it, because we have to add in acidic conditions, the more sub position. So I did that with H2O slash
It would flip the
H plus.
regiochemistry, and that's exactly.
Because I would add an alcohol in acidic conditions, and then, that would also probably be O in the epoxide, I think. And then that would give the primary alcohol that we could oxidize to the carboxylic acid. Does that make sense? I don't know if that's right. What do you guys
Oh,
think?
okay. When you said the first one, I was thinking, okay, yeah, gotcha.
Yeah, so we're gonna do all this
All
on
the
that
ones
stuff.
are-
you have to do, how do you make sure only these have one, not the other? I guess is my question.
Oh, would that give you
I don't
which
think it
both
would tie.
positions, to be honest?
Well, if you're doing
Oh, no, I
SN2
see.
for both of them, then
So
that
do
would.
2 H's then, that's what I would use.
Yeah, so I think the first one, well, I don't know if that would be the case. Maybe we use the R and OH to add the alcohol.
Well, it seems to me like
Ether hydrant.
what you can do
Oh,
is you can add the
maybe.
OH here to just this OH material. And then you can use
Do you know what I'm saying?
oxidizer to
Yeah.
make
Yeah, I know
the
what you're saying,
peroxide.
but I don't know.
Yeah.
So I think it's right. Basically, just you don't have that OH.
So that, I think that'll come from this guy, the epoxide. Did we?
Do you add another OH though? That's what we do.
Oh wait, cause we, oh yeah, cause that,
Look, 2 OHs.
that O gets protonated.
Oh, yeah,
Does
so
this,
we
does
can
this
keep
work?
going on this guy.
Oh, yeah.
Yeah, so
maybe
the first, this
first
one's
one.
fine, but this wouldn't work.
I don't know.
Or would it be the ROH/H?
What we do, I'm not sure.
Um,
Um,
I guess I'm confused why you're doing first water and then acid. Water is not basic. It's not basic conditions. Like if you did first hydroxide, then acid, that would make sense. Otherwise, I would just say water and acid, which is how it's presented, right?
Yeah.
I believe. All my sheets are up there. Do you see the difference?
Mm-hmm.
I'm not going to say it wouldn't do it, but hydroxide is a good nucleophile. Water is not. So a good nucleophile could open the ring, but then needs an acid workup. Water, not a good nucleophile. Water actually needs the ring to get protonated first so that it has an easier time opening it.
Okay. And is that what we want to do? Because we want to attack the most subposition to get that OH?
Okay, so instead of adding the NaOH,
Or would we do the, I don't know.
I'm going to leave this to you guys for now, but I love the brainstorming that you're doing. You're identifying a lot of
we add the NaOH.
options and discussing what they imply. Try both if you have the time.
If we add NaH, it'll kick off the leading group of the
I
protein.
know for this one,
and then
we want basic.
Create an epoxide. And then from there
4
with the
steps.
epoxide, we can
That's wild.
create.
It is a lot, and on an exam or a unit test, that'd be a lot of points too, because that's 4 steps to do between starting material and product, plus the 3 intermediates. That's a 7-point problem.
Oh, yeah, you're right.
You know your midterm is 70 points.
We use the
Use
KCN.
A 7-point synthesis would be 10% of your exam. One question, 10%. I actually used to have mechanisms that were worth like
Yeah, I think that'll work.
20 points, 15 points for sure, which is literally 20% of the exam.
Because that's the problem, is
That's what my biochem 2 exams were like.
Yeah, because.
A fifth of the exam came from one problem,
That's so much.
and I'd have students that would skip it.
Yeah.
They'd skip the mechanism. Why? What? That's crazy. You're going to skip 20% of the exam? You know you can't get higher than an 80 now. You know that.
Yeah.
Why? Like, try at least. Were you surprised that there was a mechanism on there? Did I not make it clear enough? And did the practice exams not show you that you'd have a mechanism? And you guys know that I
I use my
select what mechanisms.
No.
It's not like it's any mechanism you've ever seen could be on there. It's I tell you which
And
ones to
you're
know.
right, but I'm just
So
curious how
students that do that, I don't know that you wanted a better grade if you didn't come in prepared for doing that problem. Wish I had cleaned this up. My arrows are all over the place. They're not centered.
Does it matter who you
You guys might not notice that kind of stuff. Maybe you do, but I really notice it. Bugs me.
How do you even do these?
I have a software.
We do H
Once I draw a structure, I can click space and it highlights the structure, and then command arrow, and it draws an arrow to the structure again, essentially setting up a chemical reaction. So I started with methanol on this guy, and then I just went left, and then I went down, and then each time I'm just clicking and moving. Sorry, I didn't mean to distract. Keep working, guys.
So you need to sit it.
Right, yeah, that's right.
I have a question.
Hi.
How, because I think what we did was right.
Okay.
Well, I guess. But I'm just curious because we didn't really talk about like, would this flip the regiochemistry?
Flip. Well, we have two regiochemistries. Acidic conditions will open more substituted.
Right.
Basic
I mean,
conditions
like-
will open less
Like, 'cause
substituted.
this goes from dashed to wedged.
What's this?
Sorry, this methyl group.
Ah, yes. Well, the methyl group is pretty impacted by the oxygen. Do you notice that the oxygen maintains its stereochemistry?
Okay.
The alcohol was wedged.
Yes.
The alcohol becomes the ether. Or sorry, the epoxide.
Yeah.
Okay, so this is
And then the alcohol
wedged, which makes sense.
forms from the epoxide. So the oxygen maintains its stereochemistry,
Sorry, yes.
but the oxygen moves regiochemistry.
Okay.
So the methyl group is more so impacted by the epoxide. Yep. Great work.
Until it's what, like, that bond is broken with the epoxide and then it becomes wedged as well. Right, yeah, wedged.
Yep.
Right. When the nucleophile attacks, it attacks at the more substituted carbon, and it's going to. It's a backside attack.
Oh, yeah.
It is.
So
It is a backside attack.
Yeah, that's what I was thinking, and that's why I was saying that I wasn't too sure if that was the case or not, but yeah.
So, is that always the backside? Yes.
Yeah.
Yeah.
Even when it's the bromonium ring, it's a backside attack.
Okay.
Brenna, these are all the notes. On the top right are some errors
And then,
that I made on the worksheet. And like I forgot the negative charge on hydroxide. And I forgot to say we should have an aqueous workup. They are working on the syntheses right now. So if you want to catch up on the notes and then just, you're more than welcome to hop into a group. But they're starting out the easiest 2-step. And by the time you get there, they might be on the 4-step. So you can jump into them on your own if you want to as well. Thank you.
their synthesis, does it have to be a primary alkyl halide? Or could it be secondary?
It's usually primary
Okay.
because at a secondary position, we just like in OCHEM 1, secondary alkyl halide with an alkoxide usually risks competition between E2 and SN2,
Okay.
but SN2 at methyl and primary alkyl halides.
Okay.
Oh, I think you're gonna have to use that as like a.
I guess I think that we would have to do that acid catalyzed depurification to get tertiary alcohol. Maybe. Or
Because then once we have that, we can do the, oh wait, we don't wanna do that anyway. Oh yeah, we do.
yeah.
Can't we just do
Yeah, because we can't just do like a
booze and ether synthesis, because that's an alcohol to like
NBS
ether, but the
chemical
other we
as well.
can make into like.
Mm-hmm. Tricky.
So you want to do N8H in our group for the first step?
No,
Oh, for the second.
HBr excess.
That would be the second.
Sorry, you said the acid catalyzed esterification, but what if we do esterification?
Cause then we can do NaH.
Oh, it's just one
And-
more of that.
Yeah, that's what I was like, realizing.
Where does it start?
But with that HBr excess, does it kick off that, methyl?
Yeah. It turns into an alcohol.
I got that we probably,
I feel like we couldn't have that data at the part. I mean,
What if we added,
can make,
cause how do we get from this? We somehow have to figure out either how to like, cause we can either do.
is this little guy right here that makes it. So
We
we
do
can
yeah,
NaH.
so we'll
We
stick
can either do
so we'll stick
like a phenyl
I was thinking like maybe
with a halide,
if we
or we
did
could
make it
do
to
like a methyl
epoxide.
halide. So
But
it's either
how
gonna
do
add
we
this
get it
group
to
or
its
it's gonna add
half?
this group, or how do we get it to, right,
We wouldn't
but
be
there's
able to
steps
get
we
it
need
to
to
its
figure out
half.
with the other ones.
A substrate
But how
like
do
this,
you-
'cause it would be
I would just first
the secondary.
Yeah,
and
cause
then get an extra if it's not, and then you possibly add like.
Well, I'm wondering if we need like an
Unless-
alkene or like a something in the R group.
I'm still here if you got questions, guys. But the productive struggle I'm hearing is incredible.
What's the answer?
Yeah.
So what's the first step? This,
You're doing this 3-step problem?
yeah, the little OH, the tertiary OH on the right is like, we're struggling with that, guys.
I will say this one, there's like a lot of different ways you could approach it. I want you guys to recognize that there are 2 sets of the isopentyl structure. Do you see that? The 2 equivalences of the carbon chain?
Yeah,
So I want you guys to start with the alcohol and then also use the alcohol again as a reagent later in the synthesis. So I want you to transform the alcohol into a different functional group and then reuse it. Imagine you're in the lab and you take a sample of something and you start doing a reaction with it, and then you take that sample again and use it as a reagent later. Does that
Yeah,
give you some direction?
yes. So we wanna figure out how to get that there first. And then I think we were like,
Does that make it harder or worse?
wait, let me think about this.
Okay.
We
So,
could do
so we could just like,
Wait, it has to be a primary R.
that's what I thought.
So if this, that wouldn't even be,
Maybe
then
not.
wouldn't you just have
If you
like
do
this?
this one,
Do like
one, two,
yeah, so this one,
oh wait, one, two, so then go,
That's not
that doesn't work.
primary.
Oh yeah, that's
The
right.
problem
So
is
you
too
have to
though,
do
like,
the methyl
if
first.
we use an epoxide, then
But then how would the
we would
alcohol
sort of
be
have
wrong?
like,
You know,
Well, with the methyl,
that's the question of the day.
no, because the issue is that we have to
but we
somehow
have,
manage to add it.
we like green epoxide,
Because
right?
it's
And then,
Then it's what you guys need to do.
an alcohol on like a 1 and 2 position.
It
So
still
then
wouldn't be
like when
primary to
we
add that
the
that
ester,
arrow
then
group
we
onto
would
it. So with the ring, you would still
like
be able
wouldn't
to
have
add
to
it with
actually
the
correct carbon change.
H
You
or
know what I mean?
whatever.
So
We also could do
I don't think we would do,
an alcohol.
To create alcohol.
No, on alcohol. If we could figure out how to. Is there a way to? Because it is an aromatic ring.
Ready? You're stuck? On 3 or 4?
Because we can get to
Mm.
here.
Mm-hmm.
it's fine.
But
Well,
we need that guy.
yeah. So you're showing like Williamson ether synthesis to reform that.
Oh wait.
Yeah, you provided a methyl carbon, so you'll make a methyl ether.
I didn't even realize that we did that.
Williamson ether synthesis can't give you a tertiary ether
Right.
because it has to act as a nucleophile. So maybe a different way to form an ether, especially an ether out of most substituted carbon. I'm thinking there's 2 ways to do it. Although I will say, maybe it's a 2-step problem.
Hold on. Let me.
I don't think, I don't think this is 3 steps.
Form an ether?
Yeah, sorry. That might be a
And I was thinking, if we could attack
might be a 2-step problem.
but then I asked him, I'm like,
Cause then we can go
you know, I was thinking of like, and I'm like,
1, 2, 3. Map
Hmm.
our group.
Yeah.
that's like,
Is that what we're doing?
that's the only thing I can think of.
Yeah, you're taking an alcohol, making an ether out of it.
But we can make this our group whatever we want.
Depends, yeah. Depends on what mechanism you want it to go by. Because if it is SN1, then a tertiary R group is great. If it's SN2, a less substituted is better. And that process is very similar to the acid catalyzed etherification as well.
Okay.
Yeah, I'm not seeing how I could make that 3 steps. Sorry.
Is that what we do though?
I
This one?
think I think you have 2 options.
Maybe if it was an epoxide.
Okay, my thoughts are use
If it was an epoxide,
this,
then we would get that tertiary OH.
which would be,
So maybe too, what he means is like we tried to make this entire structure in a way, like that's what we first thought of, like, oh, let's just add this over side. But maybe if we add an alcohol this side, that could be, but, I'm just trying to think of like, what would be something we could do, something we can use like really quick.
Let me see, I might have something here, let's see.
This is painful.
You're doing great.
What would be CO2 with, the RP? Yes, because if you're doing, oh, you're doing this one.
which one are you doing?
Oh, you could just be CO with that.
I think that's. That would be, I mean,
I added one of them, because when you guys were talking about carbon, they're the ones
my bad. But I really love that.
Oh, a carbocation won't stay there. It would rearrange.
Am I like slightly on the right track? Like, are we able to attack that with an alkoxide?
Mm-hmm. With an alkoxide,
Well,
if you want it to be less substituted.
yeah. So how would I get that to be an alkoxide though? Would I just do O minus?
She knows how to make it an alkoxide.
Oh, with the NaH.
NaH.
So how would I, so would that be the reactant then? And then that would be, wait. That would be,
I think you're on a good track. Jaylee looks interested too. How'd I screw up that bad? Yeah. Weak nucleophile, tertiary alkyl halide, SN1.
is that like, lets us attack?
I don't know what I was thinking the 3rd step would be.
Unless there was a way to, but there's not, is there? To like add one.
And then the
add
other? No. No.
I think that's what we were so hung up on. Is
Yep.
like, how do we add one button?
Yep. How do you get there in 3 steps? Because you guys probably saw it in 2
Like,
and then
no,
just wanted to
gosh.
force it to be 3 steps and it couldn't do it. Okay. Bummer. Now I'm worried the next one's not 4. I think the next one is 3.
No, don't tell us that.
I think the epoxide would be our reactant.
I know. By the way, guys, did you notice that I said we can describe all of these as just vicinal new group plus alcohol? So I tried to do that. The organometallics, that's the hardest one to describe as a vicinal group, because what you're looking at is a vicinal new carbon-carbon bond to an alcohol. That's hard to spot, a new carbon-carbon bond vicinal to an alcohol. But then a vicinal etherol, a vicinal cyanohydrin, a vicinal halohydrin, a vicinal diol. I actually thought, since we call these hydrins, we could call this an ether hydrin, vicinal ether hydrin, instead of a vicinal etherol. I kind of like etherol though. Okay, you're all caught up? Starting on the synthesis?
Yes.
Okay. Oh, I'm gonna get you the roadmap. I got another practice assignment. One side is all reagents, one side is all structures.
Okay.
But when you guys get roadmaps, I think you know this, it's a mixture of both. You're welcome. How will you do that? Oh, you're saying this with that.
Yeah,
I see.
I didn't. It would just be with like H plus. but
Yeah.
I haven't gotten that far. I'm going backwards now.
Okay,
I'm trying
okay.
to think of how else I can do this, guys.
I'm not sure where this epoxide fits into this structure.
I'm just drawing things right now.
Okay,
you know?
okay.
But this probably wouldn't be this step actually. It'd probably be like the middle step. But it would be that, and then we'd have 2 OHs. So it would definitely have to be a step behind
Okay.
where I'm at. But I don't know where I'm going just yet. So wait, it would really be like this then. If I was doing it in order, so it would be like.
Do you think it's time to pause on this one and look at the 4-step problem?
Probably. Maybe.
Done a lot of brainstorming, and you're on a good roll.
Is the 4-step gonna be harder though, because it's 4 steps?
Not necessarily. Oh, well, let's actually check that I didn't screw this one up. Their 3-step was 2, and their 4-step was 3.
Wait, so they're already done?
No, they're just working on the 4-step.
So it would be.
Honestly, you could do it in 3. You could do it in 4, and it would make more sense, but it would still make sense. But you could do it in 3. How annoying is that?
Could be 3 or 4 steps.
True.
For our 3-step,
Hi, you guys with the STEM Center? Trio. That's right. This is great. Do you want me to pause the recording? Do you want to just talk from back there? Whatever's more comfortable for you guys. I've just got a video going of our lecture is all. Come on in. If you guys would give a few minutes to our guests from Trio STEM. Just Trio.
Just trio.
Awesome. Thank you guys.
Yes, good morning, everyone. Sorry, thank you for letting us take some time from your class today. My name is Manu,
my name is Zen.
and we're veteran associates from the TRIO program here at SLIC. And so is anyone here first gen? For those of you who don't know what first gen is, it's if your parents didn't graduate from college with Period. I'm first gen too. Okay, yes. And so TRIO is a program for first gen veteran students and low income. And so we have a bunch of different resources in our office.
Yeah, so we're a federally funded program here at Sully Community College. It's like completely free. So if you're interested in like getting more resources such as like free tutoring, one-on-one special advising, we also do a lot of like events that has like a lot of free food. And I feel like one of our favorite things we do is like out-of-state travel. We do a lot of undergraduate research conferences and also like out-of-state campus tours. So if you're interested in like going to places like New York or San Diego, like it's a really good program to sign up for if you want, you know, just that experience while being a student here at Sully Community College. We're open 8 a.m. to 4:30 p.m. in room 236. It's in the student center, so just go upstairs and you'll find us in there. And yeah, if you have any questions or just want to just ask us anything in office, we're there. So yeah, we're here to help you guys.
We have some handouts we're gonna give to y'all really quick. So
Thank you.
Thank you. Appreciate it.
thank you.
Thank you, guys.
It's a really good try. But that's not. I'm working backwards to that one.
Did you find it? Tough.
Gross.
I'm sorry.
It's okay.
I
I'm
know.
getting sick of it. It's
Yeah.
okay though. My supervisor who got me sick feels bad about it now. She called me last night and I was coughing and she's like, I'm so sorry, I feel so bad.
Well, I'm sure the air quality is not helping either.
No, and I told her, I was like, it's just taking me forever, I think, because of the air quality. But she also, she sees how bad I get when I get sick because almost every single one of my colds ends up turning into pneumonia because of my freaking asthma.
I think we do need the epoxide.
Scary.
Well, it doesn't help that I vape, so I'm like making my life 10 times harder than
No.
it needs to be.
No, I get it. I get that.
This is great.
So that's why.
I'm trying to remember everything.
Because I was like, the epoxide just like with the NaH. And I was like, wait, if we do the epoxide first,
To
we
add
could open up the ring
one of,
and keep
well,
it as an epoxide
cause
using basic
is
tension.
this
And then we can attack
vicinal or no, because it's not this?
Oh, no, cis-trans isn't vicinal. Vicinal is a 1-2 relationship. Yep.
Lisa position.
So if you're seeing an alcohol
Let me try it.
that is on one carbon and a new carbon-carbon bond on the adjacent carbon, then you've got that vicinal new carbon-carbon bond to an alcohol, which is evidence of an epoxide ring opening.
Okay, so that's what we have to do. The last step is the epoxide ring opening. Cause I get that.
So we gotta get to the epoxide.
Johnny,
Which is gonna
I was thinking, what if we made the epoxide first? But
Yeah.
How would we make the epoxide first? Would we NBS it or?
NBS is good for benzylic.
Okay.
Radical halogenation is better here. No, I don't think that would be the most effective route.
Okay.
To get an epoxide, you can either have the halohydrin Or just have an alkene. So you're trying to get to a halohydrin intermediate, but is there any way you could just get to an alkene intermediate?
We could just
Wait, but you did it right. You just didn't know it.
dehydrate.
There you go. Just like
And
Jaylee
then-
showed.
Okay.
So I was right so long ago.
Yeah, no, right? It's like
And then,
Sometimes you gotta trust your gut, right?
oh, and then
Keep
we
up
would
on
do
myself.
probably just MCPA.
oh my. Oh wait.
Yeah, because then we were thinking, oh, once we have the epoxide, we could do, we can make it an alkoxide and by opening the ring in basic conditions, by attacking with a second, wait, how do we, would that be,
Yeah, I don't know if you guys know this, but you're like cutting Jaylee off. She's completely exiled from the group. She's just looking over y'all's shoulders.
what do you have?
I think you're in the same place, actually. You just didn't draw the epoxide after MCPBA.
Where does the thumb group go?
And then from here we would do, this would be our RO minus
I guess it doesn't matter.
Mm.
in basic conditions. So it would be, because we want to attack the least sub position.
Yeah, so you've got 1 step, 2 step, 3 step, and you know what to introduce.
Wait, so does that mean that this is
So it would be,
attaching like that? If it's attaching like this, like right here?
That's what I was
and then
asking.
2, we'd have to do the H plus.
Good. You'll have to protonate it somehow at the end.
Yeah. So does that work?
Do you guys see any flaws in it?
I don't know.
Talk. What you were just gonna say. Talk to them about it, because I think you're onto it.
I did the basic condition.
Those don't look like the syntheses.
I'm going back and forth.
Which one did you start on?
I am just kind of looking at them and
Yeah.
letting things percolate.
There you go.
Until things, yes,
Brainstorm a bit,
yes.
right?
Yes.
Good.
Can you just point me in the direction of, like, if this is
Like what he was talking about at the beginning.
1, 2, 3, 4,
And then this at some point.
how does that correlate with
It's basically this.
this
Mhm.
numbering?
Sure.
Epoxide is
1, 2, 3, 4.
Okay, perfect.
I don't typically annotate 4. I would say here's 1, 2, 3. 2 and 3 is the alkene. 2 has a methyl group coming off of it. And then
Got
1,
it.
2, 3. 2 and 3 were the alkene, are now the epoxide. 2 still has a methyl group coming off of
Okay.
it.
Alkene turns into the epoxide. So,
Epoxides
1, 2, 3,
or
4.
You added a carbon. You did substitution, elimination, but you created a carbon during your elimination.
Where?
Look at your carbons, 1, 2, 3.
1, 2, 3.
Where's 1 in the starting material? Where's carbon 1?
Oh, up here.
That's not a carbon.
That's true. Well, it's because this one, I thought like H2SO4 does kick off that guy.
H2SO4 does dehydration.
Yeah. So there
It,
would still
it
be.
can't create a carbon.
Oh, that makes sense. Okay.
Now, if you're doing elimination, why make it into an alcohol to do elimination? You created a carbon as well. There's no
It's
carbon
'cause
there.
She added
Where?
oxygen at first. There is an oxygen up there where you would say.
Wait.
If we map the starting material where benzene is 1, 1, 2, 3, 1, 2, 3, 1, 2, 3,
Oh.
4.
Goodness.
And, oh, my goodness. Now, why make an alcohol just to do elimination? Can you not eliminate an alkyl halide?
Yeah.
Actually, the first elimination we learned was elimination of
Yeah.
alkyl halides. So
Okay.
you could just get to an alkene directly from the starting material if that's where you're trying to go.
Okay. What if we did that on a test though? Would you be like,
No, you can add more steps. Actually, I've been in classes where the professors say provide the most efficient synthesis,
Oh.
the least number of steps necessary. You're beginning to learn how to do synthesis, like the expectation that you can do the most efficient synthesis. That's not what I'm really worried about, but I am worried about adding carbons where carbons don't exist.
Yeah.
You added a carbon?
I did.
We all
Yep.
did it.
Yep. This one
So
here,
that this
you go from
turns.
a bond to O, and now it's a bond to carbon. Yeah? If we count this as 1, 2, 3, it becomes 1, 2, 3, 4.
Okay.
Is that better?
Yeah?
Well, so in this case, how come, I'm going back to the old,
Uh-huh.
but this one, how does this create then the alkene with that OH?
Yes, it creates an alkene.
He's
This
saying you can do that, you just don't have to.
this is the alkene that you would have made, though. Styrene.
Oh, that makes sense, okay.
What you made was methylstyrene.
Yeah.
You added a methyl group in doing it. So actually, even the way that you had drawn it, it looks to me like you just created a carbon. What you should form is something like that. What you did form was something like this. But would you agree that this is also this,
Yes.
just rotated? So you did draw the correct product, but you added a methyl group. But the way you saw it was that methyl group didn't change. But that creates a carbon, yeah.
Well, if I change it to oxygen or add whatever, then it's 4 steps.
A carbonyl?
No.
Oh.
The alcohol.
That's what I'm saying. Because you don't need to make an alcohol to do elimination.
Is
Will you
that?
show us the 3-step as well then?
It's just.
Sure.
It's just changing this into an alkene immediately from a bromine.
Do elimination right away.
This.
That makes sense.
Where's our broken one stuff?
Nice. Mimi, do you have the same glasses in sunglasses? I was waiting yesterday for them to untransition, to transition back.
Glasses at home, and so because I was so tired and in such a rush, because my partner woke me up. She was like, "You need to get up," and I was like, "Oh crap, yeah, you're right." I just ran out of the house way too quick. to
Sure.
get my glasses this morning.
Yep.
I was like, "It's fine. I have my sunglasses in the truck, so."
It just be like a.
Oh, this one's not bad.
Oh, I agree. Thank you.
Not bad at all.
Thank you.
Because I think that now
What is it? Is it secondary?
in basic conditions.
So you could use.
Basic conditions, which would create
I mean, it doesn't
epoxide
really
over here.
Well, actually,
So
so do you want the alkene form here?
this one's not fast. The other one was hard. That one's bad.
Right? You don't want it here. Doesn't matter. I think it does. Because if you use like this one, depending on which like nucleophile you use, is gonna change which elimination happens. Wait. Yeah,
Wait, yeah.
Because you have a hydrogen there. This is too hard.
You're welcome. Could you imagine just having to try and figure this out on the unit test?
Oh my gosh, I would die.
Right.
Maybe one's this hard on the unit test.
No, probably not. Maybe. Who knows?
I think if you use terpene oxide, if we were just doing it from bromine, now I'm just like going back to that. If you use terpene oxide, it's gonna do, since it's so big, I think it would form the alkene here.
You guys got this? You guys are good if I erase this part,
Well, in order to
identifying the functional groups?
you're gonna do just
You're gonna do all these attacks to the faces.
Because I just need to think about,
And then, wait, let me see something.
hold on.
No, we don't wanna do the second one. We don't wanna do the
Where's
plus
my
S one.
S6 stuff?
Because, okay, so if we do that, we attack that stuff, with the green there, we add the,
Yeah, because if you do E1, it's gonna be the most stable alkenol form, which would be between
Epoxide that we can attack this one with.
the more substitution.
Can we attack with an epoxide?
A talk. Yeah. Mm-hmm. Sorry, keep going.
Halide to substitute? Like, can we do-
Alkoxide and aryl halide?
Yeah, can we do an NAS? Does that work?
Yes. Yes. You know what? I forgot that one on my preparation of alcohols. Oh, and I guess preparation of ethers. It didn't show NAS. Bummer. Okay. Always room for improvement, isn't there?
I mean, sorry, the,
Oh yeah, you just have,
bromine
you don't
into
need
the-
steps for like
Yeah, that's what I'm
Yeah,
saying.
because we don't want to carbonate it.
Well, you can
We
use
want
two
to get-
Epoxide, and that will create the,
See, that
but
one
there's
wasn't
gonna be
bad.
a
The second one,
right? 1, 2, 3,
the 3-step one, that took,
That's just what I'm saying, is
That
you
one
want
was
it to go
tough.
this way, not this
because that one
way.
had the epoxide,
This
and
one
the
this way?
epoxide too, but.
It's gonna create Epoxide here,
instead, like closer to the green.
Yeah, because like
And
when
then-
we do the epoxide,
yeah.
epoxide, so
Right.
we can do NAS with the, to get that last group right here.
oh, I see what you're saying,
But I guess that's just what I'm trying to figure out, like, does it matter where it forms? John?
Hello.
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 I'm just trying to figure out if it matters
That's not 3 steps.
which side the alcohol
Well,
this one.
of the last one, the 4-step?
Yes, of that.
You're saying the final alkene?
No,
The first alkene
this one.
only has one place to go.
How?
Leaving group,
Uh-huh.
beta hydrogen.
Why can't it be the other hydrogen?
Well, let's look at it.
Oh, it's arrow.
No hydrogens at that carbon. Yeah, that carbon
Double bonds, okay.
has no hydrogen on it.
Wait, what is it if it's just a ring that's not arrow?
Cyclohexane.
Is there, can you like abbreviate it?
Oh, there are different abbreviations. Cyclohexane is
Okay.
CY. CP is actually cyclopentadiene,
Okay.
and oftentimes it's actually the
But you
cyclopentadienyl
just
anion.
draw it if it was probably just a ring that wasn't.
Yeah, I'll show you guys a reaction where I'll abbreviate CY, cyclohexane as CY.
Well,
But-
then it doesn't matter.
True, if it's benzene, it gets abbreviated more often.
Okay, well, what if it was, now I'm just thinking about it, if it was like
Mm-hmm.
cyclo?
Tert butoxide will take your alkyl halide less substituted.
Does it matter which side it's on though? This one, so like if it was like
To get to
like
this,
this,
yeah, I mean,
to get to this final product,
so then it's gonna go what, like
It's gonna be weird having everyone just using
like that?
it would. It would mean now your more substituted position is the carbon of the cyclohexane,
Uh-huh.
and your less substituted is the secondary carbon
So
off
then
of it.
it'll-
So you'd get a very different
Product.
product, a structural isomer. All right, should we go through them? We've got 20 minutes left.
Regardless, sure.
Can you believe it? 3 problems.
That's the only form.
The third
Took about an hour.
took like all of our
yeah,
time.
that one was it.
That one's rough.
Do you feel like you gained anything from this exercise?
Yeah.
What did you gain?
Mental disease.
Yeah.
Dizziness? A mental disease?
Decrease self-confidence.
You what? You gained self-confidence? You didn't gain self-confidence.
Nightmares, I gave nightmares.
That's too bad.
Just kidding, John, this was so fun, I loved
I
it.
gained a Rice Krispie treat.
Again, yeah, me too. That had nothing to do with me. I don't care that if you enjoy it or not. I care whether you are more prepared for the midterm next week because of it or not. And do you feel like you learned anything during this period? What do you think this exercise helped you realize?
Epoxides are magical.
Epoxides are magical.
There's multiple ways to do the same thing.
Yes. There's not just one correct route. Most of the time, there's a lot of different ways you can get something done. Sometimes it adds on more steps. Sometimes it just means using a different reagent. Sometimes two reactions, different reagents, lead to the exact same product. We actually already saw that. Alkylation of an aromatic ring. We can use Friedel-Crafts alkylation, alkyl halide with aluminum chloride. Or we can use an alkene in acid and get a carbocation that way. All right, the first one, when you guys were going through it, one of your main questions was, how is it the methyl group starts dashed and ends wedged? How am I going about that? Well, more importantly was that the alcohol started wedged and that same oxygen ended dashed. So this was a two-step problem. We can work forward and backwards. When I look at this backwards, what I see is a vicinal cyanohydrin. I've got a nitrile and I have an alcohol right next to each other. And they're anti, which is evidence of the backside attack on the epoxide ring. And the nitrile, which would be the nucleophile, the nitrile has attacked the more substituted position. So this must have happened in acidic conditions, and acidic conditions for cyanide is HCN. It must have attacked an epoxide, and the epoxide must have been wedged. Now, why do I know that the epoxide must have been wedged? Well, the nitrile does a backside attack, so the nitrile will be dashed to the wedged epoxide. But also, because my epoxide has to form from this vicinal halohydrin, and when the alcohol gets deprotonated and kicks off the halide, it stays wedged. Epoxides have to be syn. An epoxide can't be above one carbon but beneath the other carbon. That would actually mean that the oxygen is in the middle, which isn't up or down either. That's just in the middle. So it's got to be syn, and the alcohol here is forming it. The key part that I was looking for you to learn here was HCN as opposed to KCN followed by H+, because of the regiochemistry. In this bottom one, we've obviously got an epoxide, which means there's a lot of things we can do to it. But I'm thinking about this final product. Now, maybe it's useful to map our carbons here and say there's a methyl group, carbon 2 in the epoxide, carbon 3 in the epoxide, a methyl group, carbon 2 and carbon 3. And notice that carbon 2 has a methyl group coming off of it. So I think that carbons 2 and 3 of the epoxide have become carbons 2 and 3, the alcohol and the carboxylic acid. I don't know a way to get a carboxylic acid from an epoxide, but I do know how to get a carboxylic acid from an alcohol. Is this how you guys thought of it as well?
Yep.
Carbons 1, 2, and 3, and that means 2 and 3 is being opened from an epoxide into, how would you describe this functionality? Think about the terms I had on the board earlier. Vicinal diol. A vicinal dialcohol. And then I oxidize into this carboxylic acid, so I need a strong oxidizing agent. Jaylee, how come only one of my alcohols get oxidized and not the other? It's not a tertiary carbon. Tertiary alcohols can't get oxidized. There's no hydrogen for the carbon to lose, so there's no place to put an extra bond to oxygen. And then how do I get here? Well, I don't know. Did I add alcohol to the less substituted carbon, or did I add it to the more substituted carbon? Both, actually. It doesn't matter if I approach this problem by doing first hydroxide with an aqueous workup, or if I just approach this as water in acid. Either way, I'm going to get the exact same thing. I'm going to get a vicinal diol, because it doesn't matter which alcohol came from the nucleophilic attack. It just matters that I get two alcohols, a vicinal diol. Remember that on your unit tests and exams, these are typically 2 to 3 step syntheses, so the 4-step ones, those are really a stretch. And a 2-step synthesis should be the easiest kind, because you just have to identify one intermediate and then figure out how to get to and from that. All right, I said this one was supposed to be 3-step. I can't think of a way to make it 3 steps. I think it's actually 2-step. What you guys saw was an ether, which means there's really only one thing that we can do with it: cleave it. Cleave the ether. And we know that aryl ethers always become aryl alcohols. We can't do an SN1 substitution of that aryl alcohol. Now that I have an aryl alcohol, I can make an ether. And there's 2 ways that we could do this. One of them would be acid catalyzed etherification. If I have an alkene and acid, the alkene will form a carbocation on the most substituted carbon, which means there's actually 2 alkenes, 2 structural isomers that could form the same carbocation. And then the alcohol attacks the carbocation at the most substituted position and forms our ether. Or I could have done this by SN1, in which case a tertiary alkyl halide breaks to form a carbocation, which the alcohol then acts as a nucleophile on. I'm not sure what I was trying to go for with it being 2 steps, with it being 3 steps. The next one, what I wanted you guys to pick up on is that if you map the product, you essentially get 2 equivalences of the starting material. Notice that carbon 2 has a methyl group, carbon 2 has a methyl group, carbon 2 has a methyl group. Notice that carbon 3 has the oxygen, 3 has the oxygen, 3 has an oxygen, but now 2 does as well. How would you describe the functionality of this product? A vicinal etherol, or a vicinal ether hydrin. Next to each other, I have an alcohol and an ether, vicinal etherol. So that says, get an epoxide in there and open the epoxide with an alcohol to make the vicinal etherol. Now the epoxides typically form an alcohol, and the nucleophile then has attacked at the less substituted carbon. The ether formed on a secondary carbon, the alcohol on a tertiary carbon. So that tells me what type of conditions I need. I need an epoxide, and I need that epoxide to be attacked by something negative, by a basic nucleophile. I want to open the epoxide from the less substituted carbon. So that means first nucleophilic attack, second acid catalyzed workup. Not acid catalyzed, acid workup. So now I need to make an epoxide, and I can make epoxides from alkenes, and I can make an alkene from my alcohol by doing acid catalyzed dehydration. Don't forget, acid catalyzed dehydration forms, it's E1, so it forms the most stable alkene. And there are two possible alkenes. The one that we form is the most stable. We could use MCPBA here. We could do a two-step halohydrin and then elimination with sodium hydride. And we could, if we wanted to, show how to form this alkoxide from the starting material alcohol. That wasn't really a necessary part of the synthesis, but this alcohol becomes the alkoxide to react with the epoxide that we made from that alcohol. Our last two were meant to be 4 steps, but the first one I saw being solved in 3. So what I want you guys to notice here is when we map our carbons, we get a new carbon-carbon bond vicinal to our alcohol. New carbon-carbon vicinal to an alcohol. That again says epoxide ring opening. Epoxide ring opening with a nucleophile. You can see carbon-3 in the starting material. You can see carbon-3 in the product. Carbon-3 is bonding to an alkene group. So I want my alkene to be the nucleophile. Oh, no, I was wrong. This is 3 steps, isn't it? You, right, it was supposed to be 4. Right. Epoxide gets attacked by my nucleophile. Four attacks 3. Now I've got this longer chain. Now I need to get to an epoxide. Once again, the epoxide is easily formed from an alkene, but I don't have an alkene here, so I need to create an alkene. Tert butoxide works great. And this time I'm going to show the epoxide forming with just generic peroxy acid, RCO3H. There were more steps that you could put into this. You could substitute the bromine for an alcohol and then do acid catalyzed dehydration and then do the epoxidation. But there's not really a way to form a halohydrin. I know you guys were looking at this reaction trying to say, could I put a bromine vicinal to the alcohol to make the epoxide by this elimination, this deprotonation and elimination? You don't need to, because if the halogenation worked, that just gives you one intermediate, then you have to do NaH. So you might as well just form an alkene and make the epoxide that way. I think you guys could have said the same thing here. Is there a way that I can get an alcohol there so that I can have a vicinal halohydrin so that I can do elimination to the epoxide? You don't need to, because you can just form an alkene and get to the epoxide that way. All right, in the last one, 3 steps. Okay, so I really did a great job on this. What I want you to see again is a vicinal new carbon bond, but this time to an ether. So the ether must have been formed after an epoxide ring opening. So I'm going to start this time by saying let's just get to the epoxide. Now that I have the epoxide, I can add that new carbon group. Carbon 3 needs to be attacked by an aromatic ring. So I'm going to introduce an aromatic ring as a nucleophile. I want you to notice that when I did the epoxide ring opening, I decided not to show the aqueous workup. I could have, and then I would just need to do a Williamson ether synthesis, use NaH to deprotonate that new alcohol. So if I'm going to protonate an alcohol just to deprotonate the alcohol, I'm going to decide here not to protonate. You guys are okay with that? I'm skipping the acid workup because I'm going to leverage this alkoxide intermediate to do a Williamson ether synthesis onto this aromatic ring. The alternative there is that you would have to say first epoxide ring opening, then deprotonation and NAS. So you're just doing something to immediately undo it. So rather, we just won't do it. Saves us time and energy, saves us on reagents. And you may come across that where I give you a roadmap and I intentionally say no aqueous workup. Remember, in our class, we never assume an aqueous workup. We always explicitly show an aqueous workup. So if we don't show an aqueous workup, then we need to look at, investigate what it would actually look like without the aqueous workup. I want you guys to feel comfortable with both. All right, the roadmap, I will post an answer key for it later today. But the benefit of the roadmap is the productive struggle. Try to go through as much of them as possible to try and get all the answers before you lean on to an answer key for it. Deal? All right. Thank you guys for your time. Good luck on the unit test this weekend. You know what is Tuesday? A review day before the midterm. So come with questions on Tuesday. Wednesday, where do we meet? In here. What time does the exam start? 8:05 on the dot. I'll be here like normal before 8, but that 8:05 gives everybody a little bit of time to get in and get settled. And we've got 90 minutes, so from 8:05 until class runs out. And you can bring handwritten, I know a lot of you take notes on your tablets, handwritten sheet of paper, 8x11, just one side. Save that, because then you can bring it to the final if you want to, as half of your cheat sheet for the final. And revise, revise, revise. Go make a cheat sheet tonight. Then make a cheat sheet on Saturday night. Then make a cheat sheet again Tuesday night. But don't make your cheat sheet Tuesday night. Start now. Keep revising it until you bring it in. That's how you know you won't need it. Thank you guys for your time. See you later today or next week.